And Francesca, you can get started. Thank you.
Okay, thank you. As Sam already mentioned, I waited long enough to give this talk that we already had the masterclass, and I don't need to tell a lot about particle filtering and state space models. So I will have just one slide about that, but if something is not clear, please do ask me, because I've been a bit, vague about what we mean with particle filtering. This is an extension of it. So of course, if the particle filtering slide I have is not very clear, the extension is gonna be even less clear. Yeah. Okay, so this is the famous slide about state space models and particle filters. State space models, I would say that they are graphical models in which you have the latent space X, which evolves in a Markovian fashion and has some sort of transition density F. And associated to each of these x's, which evolve in time, we have observations y, which are conditionally independent, and they have some likelihood g. So this is usually the way we write a state space model. We have the transition density and we have the likelihood for the observations, and we might have an initial distribution or the initial state might be fixed. It doesn't really matter for the purpose of this talk. And there are a lot of quantities that we might want to estimate given a state space model. What I'm interested in is the filtering distribution, which is the distribution of the last state given all the observations. The reason why we start with filtering is because once you have a good algorithm to perform filtering, you can do smoothing, which means you can approximate the distribution of the x's from time 1 to t, given all the observations. And if we have the smoothing distribution, you can do parameter estimation. So let's say that these f and g depend on some theta, which is unknown. If you can get the smoothing distribution, you can estimate the theta. So in a way, developing an algorithm doing filtering can be seen as the building block of all these other quantities, all these other algorithms that you might want to build afterwards. And because this is a fairly common and known problem, there are, of course, a lot of algorithms to solve it. I mentioned over here 3 of them. The bootstrap particle filter, which is the simplest one, and the one we also discussed at the masterclass, is a particle filter in which we start with a population of n particles sampled IID from mu0, and then we just follow the dynamic of the state space model. So we add a new state using the transition density, and we use the likelihood to assign each of our particle a weight. And depending on how good or bad this weight is, we decide if we want to keep the particle or get rid of it. You can imagine that this strategy works up to a point. So if you have very complicated models in the sense that the observations are very informative, it doesn't work too well. And we can do better. And some examples of this doing better are the guided particle filter and the auxiliary particle filter, which we also kind of mentioned in the masterclass. So why, if we already have this type of algorithms, why do we need new one? Because the problem that we're interested in is a bit special in the sense that is what I call a spatial state space model. So this is just a representation of the latent space, the axis that we had in the previous graph. We have time on the horizontal axis, and now the state space is actually this sort of grid. So each one of these points is one component of the state space. They are placed on a grid. So we can imagine that there are spatial dependencies in a sense that neighboring points will be highly correlated, and nodes in this grid which are far apart will have less correlations. These type of state space models typically appear when you discretize PDEs, for instance, in weather forecasting problems or meteorology. We heard some applications to stream of waves in the ocean. Other examples are, for instance, when you want to measure the air quality in a particular city, let's say London, and you have sensors placed around London, and you want to use the observations given by these sensors to perform inference on the quality of the air in a given location. And clearly, when you think about placing sensors on a city, you can imagine that neighborhoods which are close will have similar characteristics, but neighborhoods which are far apart might be very, very different from one another. And so this is the type of space-based models that we're interested in. You can also guess from this picture that they tend to be fairly high dimensional because we have grids. This is just a 3x3 grid, so a very tiny one. But we are talking like 100 sensors, so or 1,000 sensors. So you get very high dimensional latent states. And we know that the bootstrap particle filter kind of collapses when you have very high dimensional problems. And because this is a very common problem, of course, there are already solutions out there. I'm mentioning the three most closely related over here. So probably the very first particle filter using some sort of spatial information is the block particle filter, which was developed as a theoretical algorithm more than anything else to show that basic particle filters suffer the curse of dimensionality. But the idea behind it is that if we have a very high dimensional state space, we can partition it into blocks. We can apply a particle filter to each of these blocks. And then if we take the product of these filters, we get an approximation of the full filtering distribution over the whole state space. If you think about it for a second, this idea might give you an approximation, but probably not a really good one, because you're kind of assuming that the blocks are independent. And we know that is not the case. But besides that, because you are introducing these artificial blocks, it can be proved that this algorithm is not consistent, which pretty much means you have no law of large numbers. So it's a kind of a property that you want for an algorithm, that if you increase computational budget, you're going to get closer and closer to your solution. But in this block particle filter, there is a bias due to the fact that you have blocks, and depending on the size of the blocks, this bias is bigger or smaller. So this was the first idea of using spatial information. As I mentioned, it's a theoretical algorithm, so it's not super surprising that it doesn't work in practice. But of course, starting from there have been other developments. The second one that I mentioned over here is the space-time particle filter, which again uses a similar idea. So we decompose again the space dimension into smaller subsets, which they call islands instead of blocks. We use particle filters on each one of them. And then instead of just taking the product, we perform one extra important resampling step. So this extra important resampling step gets rid of the bias. Because now we are not just taking the product, we are sort of using the product as a proposal for an important resampling step. So it is asymptotically consistent, but because of the particular structure, like when you decompose into these smaller subsets, you will have a certain number of components within each subset, and you need to be able to write down explicit expressions for these marginals. So this is the filtering distribution of time t of component I, given all the previous components. This is also given the observation and the past. So in some cases, these are quantities we have access to, and we can implement the space-time particle filter. But if we don't, then we can maybe approximate them, but we incur in a similar problem. If we are approximating these quantities, we cannot really be sure that we get asymptotic consistency. I mean, no one proved that if you use an approximation, it is asymptotically consistent. Maybe it is, I cannot say. And the last one I mentioned over here is nested sequential Monte Carlo, which, as the name suggests, they use two levels of a sequential Monte Carlo to approximate a quantity that you don't know. And so they decompose the state dimension and apply a smoothing algorithm to it. So if, as I mentioned earlier, the smoothing means we want to recover the distribution of x 1 to t. And so they replace this 1 to t, which in regular smoothing algorithms is time, with x component 1 to component d. Of course, this kind of works, it works quite well, but it's somehow limited to models for which you can write down analytic expressions for the backward simulator. So at the end of the day, both the space-time and nested, they require a model which factorizes enough. So when you write down the joint distribution of state and observation, you need them to factorize. So the likelihood, for instance, cannot be that you need to be able to factorize the likelihood into smaller blocks. So the product of several densities, one for one part of the state, one for another part of the state, and so on. So they are somehow limited by these requirements. What we propose instead is to, well, still use a decomposition of the state space, which then we embed into the divide and conquer paradigm that Adam discussed at the masterclass, and I'm going to briefly review in the next slide. In this way, we only need to evaluate the joint density of state and observation. We don't need expressions for the marginals. If we have them, we can use them, but it's not a requirement. So this is just to give the intuition of how this divide and conquer SMC for filtering would work. So let's say we are at time t and we want to estimate the filtering distribution at time t. We have observations, but instead of targeting the full filtering distribution, which in this case is for a state of dimension 8, we start by targeting its one-dimensional marginals. So we want to recover the filter of the first component given all the observations, the second component given all the observations, and so on. Because these are one-dimensional, standard particle filtering ideas still work. So at the end of the day, what we do is just importance sampling at the leaves of this tree. And then to recover the full filtering distribution, we start merging these marginals, low dimensional marginals. So whenever the branches of the tree converge into a node, we want to now estimate the joint low filtering distribution of component 1 and 2. And we have information on the marginals, so we kind of expect that if we know the marginals, we can guess where the joint is. That's pretty much the idea. The way in which these merging steps happen is according to the divide and conquer paradigm. So it's basically a combination of importance weights. But this is a very simplified example because I'm always going to assume that my state space as dimension, which is a power of 2, so I can write down everything on a nice binary tree, is not a requirement. You can imagine being a power of 3, a power of any number, or also not being a power of a number at all. You just maybe, let's say that the state is dimension 7, I'm gonna have this tree exactly as it is now, but remove maybe the first component. I have a dummy node over here, which doesn't contribute at all to this first node over here. So this construction that I'm gonna present can be applied to any D, but for simplicity, we only looked at 2 to the power something dimension. So what is this divide and conquer SMC? In one line is an extension of standard SMC in which instead of moving our inference problem in a linear fashion, which corresponds to time, we use a tree. So standard SMC, it works fairly well with state space models because we move forward in time, in discrete time, one step at a time. And every time that we move forward in time, we perform this importance resampling step. Over here, we do the same, but we do it on a tree. So this is the tree that we're going to use. And of course, if we think of a tree in which every node only has one child, then that's back standard SMC that you get back. In here, you can imagine that the problematic bit is when the merging occurs, because that's the difference with standard SMC. In standard SMC, we have no merging of different distributions. We just evolve the same particle population over time. In divide and conquer, when we get to this node, for instance, we have a particle population coming from 1, a particle population coming from 2, and we have to put them together somehow. So to give a bit more detail, at leaf nodes, as I already mentioned, we just do a simple importance sampling step. So we propose using some kernel that we pick, and then we compute the importance weights, and we obtain a weighted particle weighted particle population, which approximates this gamma u, which in the case of the previous picture is just the filtering distribution for one of the one-dimensional marginals. So at the leaf, all good. There is nothing new. We follow the usual importance sampling strategy. When we move to a non-leaf node, we need to take care of the merging before. So if for instance, if you look at the last 3 steps, you see that we have a proposal step, we have a weighting step, and we have a resample step. So that's what you would do in standard SMC. And I'm going to expand a bit on those in a second. But the very first thing that we need to do is to take into account the presence of 2 particle populations. So we have one for children 1, for child 1, and 1 for child 2. We know that each of these particle populations approximate a one-dimensional marginal. So if we want to approximate a 2-dimensional join, it's fairly natural to just take the product of the 2 marginals, which is what happens over here. So with this gamma calligraphic CU is just the product of the 2 marginals over the 2 child. And we obtain this estimator, which has n² cost, because we have 2 n-dimensional particle populations and we mix them up. This is computationally quite heavy. So what happens in practice is that we're going to use a lightweight version of this, building the product of the marginals to avoid the full n² cost. I'm not going to go into the details of that, but if you want to know more, I'm very happy to discuss. I just wanted to mention that you don't have to have this n² cost. You can do something which is smaller than that. Even just n linear in the number of particle cost, it is feasible. So let's say we built this product. We propose, because we want to mix a bit this particle up. You can see this as the MCMC move that you do in like SMC sampler kind of setting. We want to make sure that we don't end up with a lot of copies of the same particle. And then we reweight using what in the original paper, divide and conquer paper, were called mixture weights. What these weights do is that they take the product of the marginals to which we apply this kernel, and they measure the distance from the product and to the joint. So in a way, this is an empirical version of what copulas do. This is just to give the intuition. It's not rigorous at all. But if you take the product of the marginals and you want to obtain the joint, you just need to account for the mismatch between the 2. And we do this by using weights. So we do this in an importance sampling fashion. And these other weights are just the weights that we had for each child. And once we obtain these weights, we just resample to get a population of size n, because we don't want increasing dimension of our population. So if every time we build this n² and we don't resample down to n, we're going to end up with an exponential increasing number of particles, which is, I mean, in principle, I think it would be nice. In practice, you can just not implement it at all. So we need to keep the number of particles under control somehow. the novelty with respect to divide and conquer SMC standard version is that now we not only move from leaf to root of a tree, we also move forward in time. So our target distribution evolves in time and space. So it's a very, very extended target. I'm showing over here just the first level of this extension that we need to do to cast everything into the SMC framework. So basically what we have is, if we are at time t and we are at node u of the tree, we take all the past, which is this first p of x1 to p minus 1, and then we add the components which are in node u of at the current time. So if we were at the leaf node, we would just have all the past plus the, let's say, component 1 at time t. And as we go up the tree, we keep the past there, but we add components as we move up the tree until at the root we recover all components. And so the product of the past and of GF for all components is just the filtering distribution. There are a lot of other auxiliary distributions that we need to define in order to just write down a valid algorithm, but I'm gonna like hide those under the carpet and pretend that that's the only distribution that we need. I hope that the intuition kind of works. We need to move forward in time and in space. So if you think about, we have this tree, we move from leaves to root, and then we move forward in time and we go down to the leaf of the next tree. That's, if I had to represent it with a graph, that's pretty much of this divide and conquer SMC for filtering would look like.
May I have a question?
Yes.
So if you go back, I mean, as I understand it, for this, you need like each dimension, so the likelihood to factorize with respect to dimension, right?
So
is that true?
I think I had the same comment from Adam, and I think is not true, but the reason why it seems like it's true is because what I wrote in the last bullet point. In practice, this GTU, FTU are like writing the guided particle filter. You don't use the dynamics, you use something different. So you could use any G and any F over here. They don't need to come from G, T, and FT. As long as once you reach the root, they are equal to GT and FT.
Okay, I have one more short question.
Yes.
If you have like for each dimension, you have weights and particles for each dimension, why do you necessarily get rid of all those weights? Is there not a way to use, because what you do, you go up the tree, you merge the weights somehow, right? That's what happens. Is it absolutely necessary, or can you actually, because if you just use the mean weights for each dimension independently, is it not consistent, or is there a problem with that?
So you mean once I compute these weights over here?
Yeah, so do you necessarily, because you sort of merge weights and you lose some information, I guess, right? What I was saying, is there a way to use all the independent dimension weights without merging them or not?
So I think that this step in which you merge, you can use several different ways to do this merging. One way is what they call full mixture, in which you compute all of these. So you take into account the weights in the current ones. The lightweight versions, they do something slightly different. So first you use these weights to resample separately on each dimension. And then you apply the remaining part involving the gammas. Which one is the best? I don't know. They are both, all of these are consistent because you just take into account the mismatch that you create in the following steps somehow. But which way of doing the merging is the best one, I have no idea.
Yeah, I see. Thanks.
Thank you. Okay, so this is pretty much summarizing what are the strengths and what are the weaknesses of the algorithms I mentioned. There is no block particle filter because in this space-time particle filter paper, they showed that this STPF is way better than the block particle filter. And the fact that it's not consistent is kind of not nice because you are never sure how much you can rely on your results in a way. So I already mentioned the first three. The divide and conquer SMC does not need a factorization in the model, while the other algorithms do. The cost is linear in D if you have easy enough weights. I'm finding that if you have more complicated models in which you need to use all the dimensions to compute the weights, it takes a while to go through all the dimensions to get like the expression of this weight. So officially it's linear cost in D, but then depending on how you compute the weights and you define your auxiliary distributions, you might increase this weight, this cost without actually seeing it if you only look at the pseudocode, if that makes sense. Because you have a lot of freedom on defining this gamma TU that I had on the previous slide. And if you define them in such a way that at each U, you have to make a lot of computations to get the weights, it might not be so linear in D anymore. And the last one, which I haven't mentioned at all, and I will try to explain why is the case, divide and conquer SMC, the way that I explained it now, we cannot get approximations of the normalizing constant because when we compute the mixture weights, we have a constant in there which is unknown. So you can do filtering, but you cannot get approximations of the normalizing constant in the way we described it. Okay, I'm almost running out of time, so it's good that I from now on I only have plots because these are like preliminary simulation results on a linear Gaussian model, which I know is not super exciting, but we had to start somewhere. So we look at a linear Gaussian model in which the transitions are, well, not IID, so this A is not the identity, but the sigma that we have over here in the transition density is tridiagonal. And that's pretty much me being lazy because I wanted to make sure that even in very high dimension, I can compute the Kalman filter exactly, which you cannot do if the matrix sigma is not very sparse. And the measures that we compare are the Wasserstein distance. So we basically obtain this for each marginal separately. So this is the inverse CDF of the I dimensional marginal of the true filter, and we compare it with this particle approximation and the relative mean squared error. So we have the average of our particles for dimension I, we compare it with the mean, and we normalize using the variance. Okay, so these are the plots for the Wasserstein distance. And we looked at a couple of dimensions from 32 to 2000. And we have divide and conquer with lightweight mixture because the full mixture is too costly in red. And then we have green and blue nested SMC and the space-time particle filter. These are the first experiments that I run for dimension 32. The space-time particle filter is a lot better than the others. So I was pretty upset of seeing that. It turns out that if the dimension is small enough, as space-time particle filters do work quite well, but if the dimension increases, they don't, and they are very, very costly. So for dimension 2000, I didn't even include it because it would take more than 5 days to run. And we have, so going from left to right, you have an increasing number of particles from 100 to 10,000. And well, I was pretty happy to see the results on this problem because it seems that the divide and conquer has lower variance and it achieves better Wasserstein distance for this problem. And the cost is, I mean, it's quite similar to one of nested SMC. So it seems to be doing all right for this problem. And similarly, if you look at the relative mean squared error, the picture is not that different. If the dimension is quite small, the space-time particle filter does the best. But as you increase dimension, the space-time particle filter struggles a bit. And what I found was really odd is that nested SMC does not seem to improve so much when you increase the number of particles. I think, and it's just conjecture, is because they have 2 layers of nested SMC. If you increase the number of particles in just one, this is not improving the convergence on the other layer. But this is just a guess. And yeah, there is a lot to do in this direction. We don't have theoretical guarantees for this particular algorithm. We only have them for divide and conquer SMC. And there are a lot of other stuff that I wanted to cover, but I'll leave it there, and so that there is enough time for questions and for Connor.
Great. Thanks, Francesca. I'll just stop the recording here.